let's get started right where we left off. So just a quick reminder of what we were talking about. We started a whole new unit. Actually, maybe I should go. Let's see. Let's go back to chapter 13. So we started talking about statistics for chance numbers, aka random variables. So random variables are variables that are generated by a chance process. And for the rest of the class, we're going to be talking about this idea of uncertainty, right? Every time we do a chance process, we don't know what exactly is going to be the outcome. We can think about all the possible outcomes and their probabilities, but there is this idea of uncertainty. So we looked at modeling these situations with box models, and they're kind of like conditional probability tables. The box models are going to make our lives a lot easier when calculating the statistics. So chapter 13 was all about getting you guys just familiar with creating the box models, and what they are just probability models. They're like simulations. So we're saying if we draw out of the box a certain number of times, that's the same thing as doing the random process that is given. And I told you guys that if you're ever confused, to check out the summary for chapter 13. If you're ever confused on what the answer to the question is for what does the box look like, look here and it'll definitely help. We started then, so we did that for a while, and then we said, all right, the boxes are great and everything, but what's the point? Why do we need them? Well, the point is we want to know what are we expected to get. So we can think about all of our possibilities, but the question is what are we expected to get over time if we do something over and over again? So that's where expected value comes into play. And then our expected value is kind of like with regression. We said we're going to make a prediction. It may or may not be exactly correct. How do we measure our error? And that is through the standard error. So with random variables, we're dealing with expected value standard error. Just like when we talked about just regular variables, a list of numbers, we dealt with average and SD. So we looked at the two formulas for expected value and standard error for the sum. So sums are what we're going to deal with first, and then later we might want to know what's the expected value for the average or the percent. Those are definitely the three most common statistics I see. I guess there are other ones like product, but that doesn't really come into play super often. So we're just going to focus on sum, average, and percent. So let's go to, let's see, where did we leave off? I guess, well, we did this. Let's go to our next example. So on the next page, what page is this? 126. We talked about the formula for standard error of the sum. And for standard error for the sum, it does have the square root in it. Standard deviation has to do with square root. So this is it, square root of n times the SD of the box. So let's go ahead and do, what is part B? It says to compute the expected value and standard error of the sum for 100 draws. So n is 100. And this looks really familiar, right? Part A, we did the same thing, but for 25 draws. So I would just, again, this is nice. We kind of already did all the work, right? The expected value of the sum is just n times the average of the box. Every time we draw out of the box, we're expected to get the average, right? And then n times, so n is 100, and we said the average of our box, here's our box. What was my average? It was 4. So the expected value is going to be 400. And to find the average of the box, the easiest way to do this is just to treat the tickets as a list of numbers. So the average of the box is just the average of the tickets. So add them all up, divide by 5. We can see that expected value of the sum is directly related to n. If n goes up by a factor of 4, 25 times 4 is 100, right? The expected value goes up by a factor of 4 as well. So that's kind of something to take note of. Looking at those relationships, how does the formula change based on n? It's a direct relationship. Standard error, not so much though, because we have this square root. So let's see, the standard error for the sum is the square root of n times the SD of the box. And n is 100, and we said, I gave this to you guys, that the SD was 2. And where that came from was I just took the tickets and treated those as a list of numbers and calculated the SD. We can do it the long way we did in chapter 4. But I am not going to test you guys on that. We already tested on that. So we're just going to give, if it's complicated to find the SD, we're just going to give it to you guys. You saw that on the homework too, if you did the homework for today. So what is this? 10 times 2, so I get 20. So we can see that with the standard error, it's not really a direct relationship because here it was 10, here it was 20. N went up by a factor of 4, but the standard error increased by a factor of 2, which is the square root of 4. So it says, take note that the square root law came into play. So what we said was, if n increases by a factor of 4, then we know the EV sum also is multiplied by 4, but the standard error of the sum, and the standard error of the sum is multiplied by 2. So it's multiplied by the square root of 4, which is 2. And that's just because of that square root in the formula. So why do we even care about that? The idea here is that as n gets bigger, so the more and more times you draw out of a box or do a chance process, like the more and more times you play roulette or roll a die, the error gets bigger, right? The standard error for the sum gets bigger. Got bigger, not smaller. So that's important to note. It's because the more and more you play, the more uncertainty, right? Each time you play a game, like each time you roll a die, the chances of getting a certain number, they're independent. It's always going to be 1/6, but the error is going to get bigger and bigger. So that's a good thing to take note of, and that's specifically for sum. So let's go to my next example. I do want to tell you guys, I said that as long as if it's complicated to find this SD of the box, if you have to use that long way, the 5-step method that we did in chapter 4, then I'll just give it to you. But there is a quick shortcut formula that we can use in certain scenarios. So like this scenario right here, I can't use the formula, the shortcut formula. But if I look on the next page, it says there's this easy formula for computing the SD of a box. And it's specifically if the tickets just contain 2 different numbers. So something like this. So basically, the A and B are the numbers on the tickets. So like if we have a box with just 1s and 0s, I could use the formula. If I had a box with just -5s and +5s, I could use this shortcut formula. And it might look a little complicated at the beginning, but this is always the formula that people they never have to write it down because they do it over and over again and remember it. So here it is. This I'm going to refer to as the SD shortcut formula. It has to do, if you know anything about statistics, it comes from the binomial distribution, which we don't talk about in this class, but if you know about that, that's where this comes from. But basically what it is, so you take the absolute value of A minus B. So that's the numbers on the tickets, the first number minus the second number. It doesn't matter which order you could do B minus A. It's literally the same thing because it's absolute value. And then times the square root, so this is times the square root of the fraction of A tickets times the fraction of B tickets. So in other words, you can say the number of A tickets over the total number of tickets times the number of B tickets over the total. So the 2 numerators, number of A tickets plus the number of B tickets, those should add to the total, right? Because you can only use this formula if there's 2 types of tickets. So let's do a couple examples just with these boxes so you can get familiar with using this formula. So what I would do for the very first box, there are 10 tickets, right? 5 -3s and 5 0s. So right away, I'd say, okay, I can use the shortcut formula. There's just -3s and 0s. So the SD I'm just going to call negative 3a and 0b. It doesn't matter. You could switch them up. You're doing the absolute value, so you get the same thing. Even if I called negative 3b and 0a, not a big deal. So a minus b, so I'm going to do negative 3 minus 0 times the square root of the fraction of a tickets. So how many a tickets are there? There's 5 out of 10. The fraction is just 1/2 times the 5 out of 10. And most calculators, at least the calculator I have, the TI-30, I don't know, it might do absolute value, but it's kind of confusing. I don't even want to bother with it on the calculator. So I always like to do this part first. I would say, okay, if I was going to put this in my calculator, negative 3 minus 0 is negative 3, and then the absolute value makes it positive. So what I'm going to put into my calculator is 3 times the square root of 5 over 10 times 5 over 10. And let's double check this. So here's my calculator. 3 times the square root of 5 over 10 times 5 over 10. Make sure, under the square root, I would just say don't put any parentheses because you might like exclude stuff from the square root. And I get 1.5. You guys see that? Yeah, 1.5. So kind of like the RMSE, if you go a little crazy with the parentheses, that could mess up your calculation. So I did not do that, and I got that the SD was 1.5. And really, I could get this same thing by treating these tickets as a list of numbers. So really, I have 5 negative 3s, right? So in this box, if I was writing it the long way, I have 5 negative 3s and then 5 zeros. So if I calculated the standard deviation of that list of numbers using what we did in chapter 4, I will get the exact same thing. But I like this formula better than the long way. In general, it takes less time, especially if there's a ton of tickets. Like if you have 100 tickets, that's going to take you forever to do the SD by hand. Let's do the next one. I'm going to say that there's ones and zeros. 1 is A, 0 is B. There are also 10 tickets in this box. And again, I would take the absolute value of A minus B. So A and B are 1 and 0, which is nice. That's just 1. That's an easy one. And then the fractions are a little bit different. The fraction of A tickets, so the fraction of ones is 7 over 10 times 3 over 10. And if you wanted to put the fractions as decimals, that's totally fine too. Like 7 over 10 I know is 0.7. 3 over 10 I know is 0.3. They're equivalent, so it doesn't really matter. You could do that. And then when I do this in my calculator, I actually get 0.458. So 1 times this, 0.458. So my SD is a bit smaller, which kind of makes sense, right? The spread of the negative 3s and the zeros is going to be bigger than the spread of 0. 0 and 1 are right next to each other on the number line, so the spread is going to be smaller. SD, remember, is ultimately just a measure of spread. How far are all the tickets from the average? All right, I'm going to let you guys do, try number 3, this one. Go ahead and do this one. I'll put it up as an iClicker. If you have a calculator, I'd recommend using it just because this is kind of hard to do on a phone calculator. And if you don't, just ask the person next to you. But go ahead and do number 3. I'll put this up and then we'll see what you guys get. Compute the SD of the third box using the shortcut formula. I know I can use it because I only have 2 types of tickets. Okay, seems like pretty much everyone is done. So guess if you don't have it yet. I am going to stop. And most people said A. Yay, that was good. 87%. That looks great. It should be 2.76. That is exactly what I got. 9 times the square root of, there's 34 negative 1s and 4 8s. So that looks great. All right. Wonderful. And remember that the SD can never be negative. So if you're wondering why there's that absolute value sign, it's just to keep that true. The SD can never be negative. So if you get a negative number, question what you're doing. Double check your math for sure. So let's do number 5. This is another roulette one. It says a gambler plays roulette 150 times, betting $1 on the number 10. There are 38 numbers, and the bet pays 35 to 1. What does this mean? Let's see. That's kind of strange wording. When casinos say that, that just means that if you win, so basically, if you win, you get $35, and if you lose $1. So that's what that means. Looking at this, our very first step, let's see, what do they ask? What are the expected value in standard errors for the gambler's winnings? So in order to find the expected value in standard error, it's going to be super helpful if we draw our box. So my random variable is the winnings, right? This is the thing that changes every time you play roulette. Sometimes you win, sometimes you lose. So that's that whole concept of a variable that has uncertain outcomes is called a random variable. So if I was going to draw my box, my question for you guys is, how many tickets should I put in this box? So I'm going to do another eye clicker because why not? And this one says yes. Out of all these options, how many tickets should be in my box? So think about that for a minute. We'll draw it, and then once we have it, calculating the statistics will be a lot easier. Uh-oh, I just realized something. It's not up there. What is it supposed to be? 38. Yay! Oh my gosh, you guys are so good. Yes, okay, why did I do this? I think the 28 was supposed to be a 38. Okay, well, just pick a random number. This will be a bonus eye clicker, I guess. There's no right answer. Let's see, what are you guys picking? Oh, 28. That's what it was supposed to be. Good. You guys got it. 38. Perfect. Oops. Let's get rid of this. Answer if you have it, though. Answer one just because the eye clicker is kind of weird about omitting it. So everyone answer. Here, I'll just leave it up. Why not? Okay, good. You guys knew we're supposed to draw the box for one single play. Roulette, always, unless it's like a weird version of roulette, there's always going to be 38 tickets. There is on exam 3. There's at least a couple points for you guys because we'll probably ask about roulette. And what goes on the tickets is my winnings. So I either win $35 or lose $1, right? So, and then I have to say the box model is just a probability model. What's the chance I win $35? Well, there's only one way that happens. It's if I land on the 10. And then the way I lose $1, the chance of that is pretty high, 37 over 38. Let's see what that is, 37 over 38. The chance I lose is 97%. Yee. So notice, too, this is kind of strange. The fact that we're betting on the number 10 doesn't come into play, doesn't appear in the box model. Instead, it's the probability that I get a 10, which is 1 out of 38. So the 10 itself, the number 10, doesn't appear in the box model because it doesn't actually matter that what number I'm betting on. What matters is what's the probability that I win. How many numbers am I betting on? Maybe I was betting on 10 and 11. That, again, wouldn't matter. What matters is I'm betting on 2 numbers. All right, so now let's answer our question. So expected value of the sum is just n times the average of the box. So n is 150, it's just how many times we're playing, and then the average of the box, this is the tricky one, because remember, this box really has 38 tickets in it. So I want to add up all those 38 tickets, so I know there's 135. So 35 plus, and then I'm going to do -1, -1, -1, 37 times. So there's 135, and then I'm going to add that to the 37 negative ones and divide by 38. So I remember last semester on Lon Kappa, somebody posted in the discussion boards, they're like, I'm so confused about how to find the average. And I was like, why are my students confused about averages? Like, shouldn't they already know that? And then I realized it's for these boxes, if you just think of it as, oh, there's 2 tickets, then yes, it's confusing. So just remember, this really means, like, this is a shortcut way of drawing a box that actually has 38 tickets. And to find an average, all you have to do is add up all the tickets and divide by 38. So that was, I just remember that if that's something that is confusing, then if you're ever confused on the average, basically just go back to, okay, how many tickets are in the box? I just add them up, divide by that number. And I get for roulette, a classic game of roulette, I should get -2/38. I think we saw that. When did we have class? On Tuesday. We saw it on Tuesday. So 150 times -2/38 gives me negative, I'll put this in terms of dollars, $7.89. So that means if I play roulette 150 times, I'm expected to lose $7.89. But that is incredibly exact, right? It's down to the cent. If we all played roulette in this room 150 times, we could create a distribution of our winnings. Most of us would lose, some of us would win, maybe some of us would win a lot. But in order to capture that variability, that's where the standard error comes in. Standard error for the sum is square root of n times the SD of the box. And this tells us, okay, sure, we're expected to lose $7.89, but give or take what? What's a good range? And kind of like, I guess, a preview of what's coming, kind of like we did with regression. We could give percentages, like how confident are we that our estimate is correct? We can do the same thing here. If I just add and subtract one standard error, I can use the normal curve to say how confident I am. But that's coming soon. For now, let's just measure this variability. So square root of 150 times, the SD of the box here, it was not given, but there's only 2 tickets, so I can go ahead and calculate it. So there's only 35s and -1s. So that's my A and B, 35 minus -1. So I'm using this thing again, 35 minus -1. Times the square root of, and then it's the fraction of A tickets. So the fraction of 35. So in other words, you could think of it as, what's the probability of getting 35? 1/38. Times the fraction of -1s is 37/38. So not to be confused with, another common mistake I see is people will put, oh, the fraction of -1s, is that -1/38? No, because that would make me have a negative, that would mess up everything, because this is negative. So it's just how many, it's what's the chance of getting a -1 is a good way to think about it. So calculator time, let's see, 35 minus -1 is 36. There we go. 36 times the square root of 1/38 times 37/38. This is really hard to see, but 5.76 should be my SD. So that's my SD. And let's plug it into my standard error, 5.76. And that gives me, I'd have to put that into my calculator, but this is a big number, 70.54. So the standard error is huge, which means my winnings, if I do -7.89 plus or minus 70.54, you could either win a lot, lose a lot, or win a bit. So this standard error, right, because gambling, there's so much uncertainty. The error is really big. You never know. So I would say, if I was interpreting this, I'd say we'd expect to win. I guess when we get negative, we're not winning, but you get the idea, right? We'd expect to have a net profit. We'd expect to win between, I would say, -7.89 plus or minus 70.54. So if I put that in terms of, like if I actually did -7.89 minus 70.54, I get -78.43 2, and then if I did negative 7.89 plus 70.54, 62.65. So I'm expected to either to make a net profit of between about negative 78 and positive $62, which is, I don't know. That's such a big range, so much uncertainty. Kind of crazy that that's a thing. But our expected value is negative, so that's not good. We're expected to lose. But that's how you would interpret it. Because sure, anyone, just like a z-score, anyone can plug numbers into a formula. The question is, what does it mean? And that's exactly what it means. It's what are we expected to win, give or take what? So last question, last example in chapter 14. This is kind of similar to one we did the other day. It says a multiple choice test has 25 questions. Each question has 5 choices. If you guess at random on all 25 questions, what's the expected value in standard error for the number of correct answers on your test? So number of correct answers is our random variable, right? Because that's going to change. If we're guessing, that might change every time. We know we can figure out what are we expected to get, give or take what. So let's see. I know that for my expected value of the sum, I need n times the average of the box. And then for my standard error for the sum, I need the square root of n times the SD of the box. So my question for you guys is, so n I know right away, right? It says there's 25 questions, so that's my n. This is 25. So the next question is, we need to draw our box and find the average. So I'm also going to have you guys go ahead and try that out. We haven't asked a question. I haven't asked an iClicker question about average. I promise this one has the right answer, and I will put it up. So the question is, let's not do that one. Let me close this. Stopping that, we can see. Most people said C for the random one. Okay, what is the average of the box? So this one, I see the right answer. I know there's one. So you'll have to draw your box first and then find the average. And it looks like most people said B. But what else? 1E. The other ones, kind of a lot of people said the other ones. So let's look at our box first. So remember, you always want to draw your box for one single draw. So in a multiple choice test, one single question. In roulette, one single spin of the wheel. So we said each question has 5 answers. So there's one right answer, and if you get a wrong answer, you just get 0 points. So I drew my box like this. You could draw it either way. And then the average is just you're going to add up all the tickets. 1 plus a bunch of zeros divided by 5. It should be 0.2. So the most common answer was correct. But that's where it came from. If it said, if you put 1 over 25 in particular, remember, it's super complicated if you try and draw your box for the whole entire scenario. Because 25 questions, 5 possible answers, that's going to be a lot of tickets in the box. It's easier just to think about one question, and then we would say, all right, we would draw 25 times out of this box with replacement so that our probability of getting the answer right remains the same. So I found the average was 0.2. I plugged that into my expected value, and I'm expected to get 5 answers correct just by guessing. So that's what I'm expected to get. But again, 5 it's so exact. Let's actually put it in terms of a standard error. So n is 25. The SD of this box, again, I can use the shortcut formula because there's only 1s and 0s. So I would take the absolute value of 1 minus 0 times the square root of the fraction of a ticket. So the fraction of 1s is there's 1 out of 5 tickets, times the fraction of zeros, or the probability of getting a 0 is 4 out of 5. Getting the answer wrong. And this gives me 0.4. So let's see, square root of 25 times 0.4 gives me 2. So if I was interpreting this, I'd say you'd expect to get 5, give or take 2 correct answers just by guessing. So this is definitely good to know, because like I said, I think I said this on Tuesday, there was some poor soul in this class who on the exam 2 got like way less than what you would expect to get by guessing. And so I was like, okay, this is a problem. Like, they didn't just bomb the test, it was probably graded with the wrong form. So that kind of thing helps me to realize, is this a realistic low score? Or is this totally, like, even if they guess, they shouldn't have done this bad? So that's the same kind of scenario here. But that is chapter 14 in a nutshell. So we're going to go to chapter 15, which is also still about random variables. The difference between chapter 14 and chapter 15 is, you can see it in the title. Chapter 14 is called the expected value and standard error of the sum. And then chapter 15 is called the expected value and standard error of the average and percent. So I want you guys to see how these are just a little bit different. So first we'll look at average, the expected value and standard error of the average. And the nice thing is, the expected value of the average is really saying, if I draw a bunch of tickets out of a box, what do I expect the average to be? And so the formula isn't really a formula. It says you don't need a formula. The expected value for the average, now if I'm dealing with averages, because sure, sometimes you want the sum, like if you're adding up how much money you win when you're gambling, it makes sense. You want to know what's the sum of your profit. But sometimes you want the average. Like if I wanted to know something about our class, like, I don't know, what are your guys' GPAs? I wouldn't want to add up all your GPAs. Instead, I'd want to take the average. So the expected value of the average, nice thing is, it's just the average of the box. Expected value of the average of n draws is just the average of the box. So this one's easy to remember. Here is this same box that we saw the other day. It has an average of 4 and an SD of 2. So this box, we couldn't use the shortcut formula because there's more than 2 types of tickets. So here's another example where I just give you the average, or the SD. And then it says, what is the expected value of the average of 100 draws? So the expected value of the average is just going to be the average of the box, which we know is 4. So this, I feel like, is almost easier than the other one. The standard error for the sum, so it says that we'd expect the average of the draws to be the same as the average of the box. But of course, there is going to be some variation. We won't get that every single time because we're dealing with random variables and chance. So we'd have to figure out the standard error for the average. And I just like to write these. The standard error for the average is the SD of the box divided by the square root of n. So it's like the standard error for the sum, but instead of multiplying, we're dividing. And actually, normally, this is Stat 100, this is a Gen Ed. I try not to show you guys too many proofs, because proofs, I don't know how people feel about them. But with this, I feel like it's an easy one, so I'm gonna show it really quick. So if we want to go from a sum to an average and sum are related, right? To find an average, you have to take the sum and then divide by n. So basically, to get this formula, all I did was take the standard error. So right here, standard error for the sum, I just divided both sides by n, because an average is just the sum divided by n. So if I take the sum divided by n, I get an average. And then if we simplify this, like I could leave it like this if I wanted to, but if I simplify this, so this and this are the same thing, I have the square root of n times the SD of the box, so that's the standard error for the sum. And then n, I could actually write as the square root of n times the square root of n, and then these two things cancel out. So literally, to get this formula, I just took the standard error for the sum formula and divided it by n. And here's the simplified version. So hopefully that wasn't too bad, but that's where it comes from. This one's super easy to see where it comes from. I am now going to use that to answer my question down here, 1B. So we know that we'd expect the average to be 4, because this was the expected value for the average. Anytime I ask you guys, what do we expect? Well, that's what expected value tells us. Give or take, this should be the standard error for the average. So if I was going to go ahead and calculate this, I know the formula. Right here is just SD over square root of n. So the SD of this box, this is the same box as above. We said the average was 4, and the SD was 2. So 2 divided by the square root of n was 100. So what is that? 2 over 10, 0.2. So this is saying I'd expect the average to be between 3.8 and 4.2. If I drew 100 times out of this box and averaged up all my tickets, that's what I would expect to get. All right, so there's a couple more examples, and then we'll look at percent, which is basically the same thing as average, so that's nice. Let's go to the next page. All right, so this one says 36 straws are made at random with replacement from this box. Here's my nice box. It looks good. 36 is my N. It says, what would you expect the sum and the average to be? So basically, I want to find the expected value of the sum and the expected value of the average. So sum is a review. Expected value of the sum, standard error for the sum, and then expected value of the average, standard error for the average. So I'm going to have you guys do the sum, and then the average, we can use the new formulas to do those. So go ahead for expected value of the sum. Here, I'll even do this. N times the average of the box, square root of n times the SD of the box, and go ahead and answer those. So we'll do the sum first. So I'm going to put it up. Box has 4 tickets. For the standard error, if it has 4 tickets, I need to give you guys the SD because you can't use the shortcut formula. Here it is. What's the expected value of the sum? Okay, EV sum, N times the average. So let's check. I'm going to stop. And yay, C looks good. 108, right? Average of the box was 3. If we add all these up, 0 plus 2 plus 2 plus 8, divided by 4 gives me 3. So my expected value of the sum is 108. So if I draw 36 times out of the box, add up all my tickets, I should get 108. And then the SD here, there's more than 2 tickets. So I would tell you guys the SD is 3. And then for my standard error, I know N is 36, and the SD is also 3. So 6 times 3 is 18. So that's kind of review from what we did the other day and at the beginning of class today. The average, so now instead of taking all my tickets and adding them up, I'm taking the average. So the expected value of the average we know is just the average of the box. What would I expect the average to be? Well, just 3, right? If that's the average of the box, that should be the average. And then the standard error for the average is the SD of the box. It's the same as sum, except we divide instead of multiply, divided by square root of n. So 3 over square root of 36, 3 over 6 is 1/2. Or 0.5. So these are pretty straightforward, nothing too crazy about them. The part C, though, it says, now suppose you draw at random with replacement from the same box, but this time you're not summing or taking the average. Instead, you want to know, what do we want to know? How many 2s you get. So this is a binary outcome, right? We either get a 2 or we don't. So like if I get a 2, I want to count that as I got 1 2. If I get a 0, that I didn't get a 2. If I get an 8, I didn't get a 2. So it says first our hint is if we're counting the 2s, then we have to, so counting means we're going to add them up, right? Sum, we're adding up how many 2s I get, counting them up. It doesn't say anything about average, so we don't have to deal with average. It says we should change our box to a 0, 1 box. So what I would do here, because I'm counting something different, I'm not just counting, I don't want to count an 8 as 8, I want to count an 8 as 0 2s. I want to count a 0 as 0 2s. And if I get a 2, I want to count it as 1 2, not 2 2s. So the hint is telling me I need to change my box depending on what I'm counting. So kind of like how when we did the example with rolling a die and counting how many 2s, we counted a 2 as 1 2, all the other numbers 1, 3, 4, 5, and 6 as 0 2s. So if any time you draw a new box, you want to make sure to find the new average and new SD. So I can't use the average and SD of the old box if I'm using my new box to calculate expected value in standard error. So if I wanted to draw this box, let's see, it has 1s and 0s. There's two of each, right? I have a 50% chance of getting a 2, of getting a success, a 1. So there's 4 tickets. And here, I am just going to say, so here, if I read this problem, it doesn't really say sum or average. So if the problem doesn't specify that it wants average, you can just assume it's sum. So I want the expected value of the sum because I'm counting up how many 2s I get. So n, is our n still 36? Yeah, in 36 draws. N is still 36. And my average, remember, if anytime you draw a new box, anytime you change anything, you have to change your average and SD. So my average is going to be, let's see, I would technically do 0 plus 1 plus 1 plus 0 divided by 4. Or I could say there are 2 1s plus 2 0s divided by 4. So the average is 0.5. 36 times 0.5 is 18. I guess I didn't even really need a formula for that, right? If there's a 50% chance of getting a 2, if I draw 36 times, I should get half 2s. But formula always helps, just to double check. So I'd expect to get 18 2s, give or take. The standard error for the sum is the square root of n times the SD of the box. So n is 36. And then I do need to find, I have this new box that I'm dealing with, so I need to find the new SD. And I can use the shortcut formula here because there's only 1s and 0s. So I'm going to take the absolute value of 1 minus 0 times the square root of the fraction of 1s, which there's 2 out of 4 1s, times the fraction of 0s. Also 2 out of 4 zeros. And I actually get, so this box, the box with half 1s, half 0s comes up a lot, especially for flipping a coin. So I'm just going to write this down because it might save you guys some time. But basically, so my answer for the SD is also 0.5. So anytime, if your box has half 1s, and half 0s, your SD is going to be 0.5 because basically your outside part will be 1 minus 0, which is 1, and then your fractions will be 0.5 times 0.5. Square root of that gives me 0.5. So this you'll see, as we do more and more practice, you'll see that this comes up a lot. So I thought I would just say that now if it saves you a bit of time. So square root of 36 times 0.5 is 6 times 0.5, which is 3. So I would answer my question by saying you'd expect to get, the original question was how many 2s you get. So you'd expect to get 18 plus or minus 3 2s in 36 draws from our box. So we've done some, we've done average. Now that we've done those, there is one more, which is percent, and percent is just like average. So this is really nice. So on this next page, expected value and standard error for the percent. What if I want to know the percent of something, like the percent of you guys who have class on Friday, or the percent of you guys who have taken calculus, or something like that. Average would be weird. I don't know, maybe the count might be good, but I personally like percents. So the nice thing is, just like the average, the expected value of the percent, so the expected value, I just like to use the little percent sign instead of writing it out, is just the percent in the box, just like average. So if there are 50% twos in the box, my expected value for the percent of twos I'll get is just going to be 50%. And then I wasn't kidding when I said they're exactly the same. The standard error for the percent is just the SD of the box divided by the square root of n. So same as the average. The only thing is I want to multiply it by 100 to put it in percent form. So with percents, it says multiply by 100 to change from a decimal to a percentage. So for any statistics on percents, I want your answer to be between 0 and 100%. So this is for EV percent and SE percent. So this is like the same kind of example. This is kind of an easy one for the expected value of the percent of twos. Well, that would just be, okay, the expected value for the percent is just the percent of what? Of twos in the box. So that's what I mean up here by like the percent in the box, the percent of whatever you're looking at. So there's half twos, right? Here's my box. It has 50% twos. So I feel like this one is kind of, we need to, let me show you if it was a different, so let's do here, random example, just so you guys can see how to do this if it's not 50%, because 50% is easy. What if I had a box that looked like this? Let's say it had threes and twos, it had 12 tickets, 5 threes and 7 twos. So this is a weird box, just a random box that I made up. If I asked you guys, if I said, what's the expected value for the percent of threes in the box? This one isn't just 50-50, so the way that you would find this, the way that we would do this is say, okay, the same thing I did up here, the expected value for the percent is just the percent of threes in the box. So same thing as up here. Up here it was really easy to see there's 50% twos. Even when since I'm counting twos again, I guess I'd want to use this box. The hint says to go ahead and change my box to this one. And again, there's 50% ones. So with this random example, it's not 50%. Instead, I know the fraction, right? I know this means there are 5 out of 12 threes. So that's my fraction, but I want to put it in percent. So I would just multiply that by 100% to get it in percent form. So if you have a fraction that isn't like 1 over 2, something really easy, or like 1 over 4 that you can simplify, you can just put in your calculator 5 out of 12 times 100, and I get 41.67%. So that one's a little more complicated. So I just wanted to show an example that wasn't 50-50, just so you guys know you can take a fraction, multiply it by 100 to turn it into a percent. So the standard error for the percent is going to be, we know it's the same as the average. The SD of the box divided by the square root of n times 100 to get it in percent form. So this is the same as the average times 100 to get it in percent form. Remember, I am using my new box. So my new box, we said, had an average of 0.5 and an SD of 0.5. Because I'm counting, all I care is, did I get a 2 or not? So my SD is 0.5. My n is still 36, and then I would have to multiply that by 100. And if I put that in my calculator, I get 8.33%, which is a number between 0 and 100. So it means I'm expected to get half twos, 50%, give or take about 8.33%.